Okay, so what's going to be our first step when we're looking at this? Ayla? Why do we want to know the direction vectors from the two? Okay, very nice. So it tells us a lot about the relationship between these two lines, the nature of that relationship. So in parametric form, the direction vector is the coefficients. And in vector form, it's given. And in this case, they're equal. They're actually the same. Oh, my goodness, what is going on here? They're actually exactly the same. They don't have to be exactly the same. If they were scalar multiple, if one was a scalar multiple of the other, including positives and negatives, that would be just as good. This tells us, as John said, that they're parallel. It tells us if the direction vectors are parallel. What is happening here? Therefore, L1 is parallel to L2. That's what we know. What next? Again, if you think about, it's useful to think about the possible outcomes. This is 3 space, so we've got an extra outcome that the lines could be skew. And if you think about the possible outcomes, and then you think about the properties of lines and how the properties would relate to each other in those 4 possible outcomes, we're kind of just narrowing it down, right? We're saying, is this true? Yes, no. Is this true? Yes, no. Is this true? Yes, no. And eventually you get to the end. Yeah, so if the lines are parallel, then if any point on one of the lines is on the other line, then the lines are coincident. If any point on one of the lines is not on the line, then the lines are parallel and distinct. Because otherwise they would be crossing somewhere and not parallel, and we've already determined that they are parallel. And you could pick any point, but we're given position vectors, or we're given points, so why not just use that? So I'm going to check -2, 3, 7 in L2. I use that as my point. So -12 plus 5t. I'm using the point from L1 and I'm checking it in L2. Don't use the point from L1 and check it in L1, right? So t is consistent. Therefore, my point, -2, 3, 7, is on L2. That's what I was checking, so it's true. Therefore, the lines are coincident. You want to say both of these things, and There are infinite solutions. So what you're thinking about is, what does it mean that the direction vectors are scalar multiples of each other? What does it mean if they aren't? And how do you deduce which of the four possible outcomes you would have in each case? Okay, let's try another one. Symmetric form and vector form this time, so a little bit different. It's the same process, though. There's no rule that says you have to check the direction vectors first. You could check to see if a point is on the other line or something, but it's less efficient. Checking the direction vectors is quick, and it kind of puts you either in this category or this category, and then from there you should know what to do. Okay? If the direction vectors are not, or if the lines are not parallel, if you check the direction vectors and they're not scalar multiple, you're not picking a point from one and checking it on the other. That's not really going to tell us much. You got options. You could always rewrite in a different form. Can somebody remind me how we originally developed symmetric form? Not specifically, but in general, because I think it can help you. Does anybody remember how we did that? How did we come up with symmetric form? This one on the left here.
The bottom, the denominators are the direction vector.
Yeah, good.
And then the x, the y, and the z, that's the first part of it.
Yeah.
And the numbers at the top, so the x and y, that's the position vector.
Okay, good. So that's useful because then you can get the direction vector out of it. How did we develop it though? Yeah, so we solved each of them for t. Probably we started with parametric form. And then we set, if they're all t equals this, t equals this, t equals this, I can set them all equal to each other. So sometimes when I'm working with this, I remind myself symmetric form is like t equals this, which equals this, which equals this, t equals all those things. Because then if I was solving for x, it'd be t equals this, I'd bring the 1 over, and then I'd add the 2, and in my head I can kind of remind myself where those things go. Does that make sense? So remember, these are all equal to t. So they're all equal to each other. That can be useful if you ever get stuck sort of trying to figure out where to go. What did you notice when you did this part? Hilaf? So negative 2 times d1 will give me d2. Therefore, parallel. So just like the first example, we're going to pick a point and check it in the other. So I'm going to check 2, 3, and negative 4 in L2. After the first two, I see they're not consistent, so it doesn't really matter what happens with the last one, but I'm going to do it anyway. They're all inconsistent. T is not consistent. Therefore, 2, 3, negative 4 is not on L2. Therefore, no solution. State the nature of the solution and why. Because there's different reasons why you might have no solution. It's just part of their interpretation. It helps us think about these things. The lines are parallel and distinct. Good enough? So we're noticing the pattern that the first thing we're looking for is direction vectors, right? Like that to me, if you're thinking about steps, that's the first step. Whatever form you're given the equation of the lines in, the first thing you want to do is figure out what the direction vectors are, because it's fast, and you can then use that to start to think about, well, what am I looking at? If they're parallel, now I have to figure out if they're coincident or if they're distinct. If they're not parallel, we still have two options. But between our two options, we solve it in the same way. So once you've determined if it's parallel, it's like a flow chart. And actually, you might see a flow chart somewhere. But like once you've determined if they're parallel, if they are, you're doing this. If they're not, you're doing that. And then in each case, you're interpreting your solution. This should be a 1, I believe. Yep. Okay, give this one a try. When we were talking about planes, we kind of talked about how scalar form is really useful, but we notice in this case, vector form is pretty useful. Because you're given a position vector, you're given a point, and you're given the direction vector explicitly. I mean, it's not hard to get out of parametric or symmetric, but it's a bit more straightforward here maybe. What'd you notice about these ones? This is what I got so far. How did I determine that there is no scalar multiple? Because if it's obvious, if you're multiplying by 2, it's pretty obvious. But maybe there's some cases where it's not going to be as obvious. I don't know. So I would look for a specific multiplier of 1 and then check it against the other. So if I take -1 and multiply by 2, I get -2. But if I multiply -3 by 2, I don't get -1, obviously. This one's getting bigger. This one's getting smaller. You can also just look at signs. If in this case, that doesn't help because the signs are the same, the same, the same. But if the signs are the same and then different, then like there's no way to resolve that with a constant, right? So anyway, that should be straightforward, but sometimes we start second guessing ourselves. So, check for a constant multiplier. So what do we do in this case? Do you remember from yesterday? Yeah, very good. We're going to set up little equations for x, y, and z. And then out of those 3, you could pick your favorite 2, solve. And then use that to check in the third. So for x, I get the x parts of line 1 is 10 minus 1s. So 10 minus s equals the x components of the other. So that's 14 minus 2t. For y, it's 2 minus 3s equals -1 minus 1t. And for z, it is -5 plus 5s equals -4 plus 3t. This is where I would look at them and kind of decide which form is best to put it in. And that's a very personal thing in a lot of ways. Like, not everybody's going to agree. So it's not about right or wrong. And you don't even have to put all 3 of them in the same form, because the other one you're going to do a check, but again, that's up to you. So I'm going to solve 1 and 2 and check it in 3. And I'm going to do equation 1 minus 2 times equation 2. I'm going to cheat a little bit here and kind of do it all in one step. You might want to split it up into 2 steps. But that's going to eliminate the t's. So 2t minus 2 times t is gone. Negative s minus 2 times -3s is minus -6s, which is plus 6s, so this should be 5s. And then 4 minus -6, 4 plus 6 is 10. Four into 2. We good? So this looks like negative 9 plus 10, which is 1. All we've determined there is that the lines cross at a point. And we found the T and the S that makes them cross, but that's not the solution. So you pick your favorite variable, S or T, and we're going to solve for x in each of these. So x equals 14 minus 2t. That's from here. That's from, it looks like equation 2, right? 14 minus 2t. You could do it in either, but if I did it in L1, I'd be using S, obviously. I hope that's obvious. So if I choose S, then I'm using L1. I chose T, so I'm using L2. So 2t is 2 times 3, so this is 8. Y equals negative 1 minus t, so minus 3, so that's negative 4. And z is negative 4 plus 3t. That's 5. Okay, questions? Before you go and start your practice later on, you could look at the 4 examples that we do and look at how they play out in 4 different ways, slightly different ways. I know we have one more left to do. We're going to do one more example, but like compare them. What happened here? What happened here? What was the same? What was different? To really get a sense of what each solution looks like and the order in which we do things and how do we interpret the outcomes, all of that good stuff. Okay, last one. Once again, I got that they're not parallel. Did you find that? So same as the last example, go ahead and start setting up your equations for x, y, and z. This is what I got for my first line. Is that what you got so far? Something kind of interesting happens here. And if you were seeing this for the first time, it'd be enough that it might kind of make you second guess what you're doing is right or wrong. You might get stuck. If you hadn't seen this before and it was on a test or whatever. So I'm going to add 3 and I get 5 equals 4t. So t equals 5 over 4. And I subtract 3, so 3s equals negative 2 and s equals negative 2 over 3. What happened? That's our solution. That's what we were trying to get anyway. S equals t equals. We just, because of the zeros in the equations, it was obviously set up this way. We're done. There's nothing more complicated. It's one of those funny things where if this happened, you'd be like, oh, what do I do now? And people would do this. They'd be like, I'll call this 1 and I'll sub 1 into 2, and they'd start making stuff up, right? But you're actually done here. Okay? So I'm going to call this equation 1, or actually, wait a minute. I'm going to simplify it a little bit first. Bring the t over, so t plus 2s equals negative 8. Is that right? Call that equation 1. And I'm going to check s equals negative 2 over 3 and t equals 5 over 4 in equation 1. Oh no, fraction math. I hate fractions. This is the second last day of this course and you're making us do fractions. How dare you? Thankfully you have calculators. What can I conclude? Nice. The lines are skew. No solution. Make sure you state no solution. And make sure you state why, that they're because they're skew. When you think of fractions, 5 over 4 minus 4 over 3, when you think of that, do you go back to like grade 3, grade 4 when you first learn fractions? And this is a whole plus a little bit, and that's a whole plus a little bit. But this has 1/3 extra. This has 1/4 extra, so this one's like a whole plus a little bit more. So the answer should be negative. Do you ever think about that? Sometimes it's funny how we take these things for granted. Like that's how you learn about fractions originally, is which one is bigger. Just thinking about, is this a bigger fraction or is that a bigger fraction? How many parts of the whole? And then we sort of stop thinking about it that way and we just think about it as a mechanical thing, a rule. When I multiply fractions, I do this. When I divide fractions, I flip and I multiply. And we forget about what fractions actually are. It can be useful to actually think about what they are and go back to their original nature. Anyway. Side note. Okay, so from yesterday's worksheet, there's a few more questions to try.